right, so we're on the bottom of page 11. So Spearman's row, section 10.3, bottom of page 11. Pearson's R is useful for a lot of things, but it has its shortcomings. One particular issue does stand out. So what it generally measures is the strength of the linear relationship between the variables, the two variables. In other words, what it gives you is a measure of the extent to which the data all tend to fall on a single perfectly straight line. Often this is a good approximation to what we mean when we say relationship, quote unquote relationship. And so Pearson R is a good thing to calculate, but sometimes it isn't. We're going to move on to page 12. One very common situation when the Pearson's R is not the right thing to use arises when an increase in one variable really is reflected in an increase in another variable. So increase in y and an increase in x and an increase in y. But the nature of the relationship is not actually or necessarily linear. So an example of this might be the relationship between effort and reward when you're studying for an exam. So if you put in 0 effort x into learning a subject, then you should expect a grade of 0% y. Okay, that's so your effort is x and your grade is y. However, a little bit of effort will cause a massive improvement. So just turning up to lectures would mean that you can learn a fair bit, and if you just turn up to classes and scribble a few things down, your grade might rise to 35%, all without a lot of effort. However, you just don't get the same effect at the other end of the scale. So as everyone knows, it takes a lot more effort to get a grade of a 90% than it does to get a grade of 55%. So what this means is that if we've got data looking at study effort and grades, there's a pretty good chance that Pearson R would be misleading. So to illustrate, consider this plot on figure 10.11. It shows the relationship between the hours worked and the grade received for 10 students in one class. And so again, we're going to be looking at this figure where the dashed line through the middle will show the linear relationship between two variables. The curious thing about this, which is a highly fictitious data set, is that in this data set, increasing your effort always increases your grade. It might be by a lot, it might be by a little, but increasing the effort actually never decreased the grade. So if we run a standard Pearson correlation, we can see that there's a strong relationship between the hours worked and the grade received, with a correlation coefficient of R equals 0.91. However, this doesn't actually capture the observation that increasing hours worked always increases the grade. So there's a sense here in which we want to be able to say that the correlation is perfect, but for a somewhat different notion of what a relationship, quote unquote relationship is. What we're looking for is something that captures the fact that there is a perfect ordinal relationship, okay? That is, if student 1 works more hours than student 2, we can guarantee that student 1 would get the better grade. That's not what a correlation of R equals 9.91 says at all, though. So again, we're moving through this figure of figure 10.11, which shows the hours worked and the grade received. So how should we then address this? Actually, it's easy. If we're looking for ordinal relationships, all we have to do is treat the data as if it were ordinal scale. So instead of measuring effort in terms of hours worked, let's rank all 10 of our students in order of hours worked. So then student 1 did the least work out of anyone. They did 2 hours, so they would get the lowest score or the lowest rank, which would be rank equals 1. Student 4 was the next laziest, putting in only 6 hours of work over the whole semester. They got the second lowest rank, or rank equals 2. Notice that we're using rank equals 1 to mean low rank, okay? Sometimes in everyday language we would talk about rank equals 1, which would mean actually the top rank, right? Like the highest percentile. Like if someone, yes, scored in the 99th percentile, right, and their rank was very high. So in everyday language, sometimes we talk about rank equals 1 to mean a top rank and not a bottom rank. So just be careful, because you can rank from smallest value to largest value, where the smallest value equals the lowest rank, and that is your rank 1. Or you can rank from largest value to smallest value, where the largest rank is equal to 1. There is a subscript note here that says you may also hear the term monotonic relationship. There is a monotonic relationship between two variables if the direction of the relationship is consistent, meaning that as one variable increases, the other variable either consistently increases or consistently decreases, but not necessarily at a constant rate. So that is a monotonic relationship. So again, there is a monotonic relationship between two variables if the direction of the relationship is consistent, meaning that as one variable increases, the other variable consistently increases or consistently decreases, right? But not necessarily at a constant rate. We're moving on to page 13. So just make sure you're consistent across both variables. In this case, we're ranking smallest to largest, but it is easy to forget which way you might have set things up under different circumstances, so you have to put in a little bit of effort into remembering. The rankings in this example are displayed in a table on page 13, which is table 10.3. So we have 10 students. We have them ranked in terms of hours worked and grade received. So like it's a 1-to-1 relationship. So a 1 hour worked got a grade of 1, okay, or a rank of 1. 10 hours worked got a rank of 10. 6 hours worked got a rank of 6, right? It just went 1 through 10. So the rankings in this table, table 10.3, they're identical for the two variables. The student who put in the most effort got the best grade. Student with the least effort got the worst grade. So as the table above shows, these two rankings are identical. So if we now correlate them, we should get a perfect positive relationship with a correlation of P equals +1, and that, so what we've just reinvented is called Spearman's row, also known as Spearman's rank order correlation. It's usually denoted as little p to distinguish it from Pearson's R. So if you love doing these long, tedious mathematical calculations, You can compute it with this equation on page 13, okay, where we have a little d is each participant's difference between their ranking on the x variable and their ranking on the y variable. N, big N, is your sample size. So in the example, figure 10.11, table 10.3, every student's ranking is the same for the hours worked variable and the grade received variable. Thus, all the values of D would be 0, and P would equal 1 minus, and then it's 6 times 0 divided by 10 times 99, which reduces P to be 1 minus 0. This shows that if all rankings are the same for both variables, then Spearman's row will be +1. Like Pearson's R, the range of possible values of Spearman's row goes from -1 to +1. So if you have a small sample size, doing these calculations by hand, it might not be so bad. But you can imagine how challenging this would be with the larger sample size. Therefore, in real life, we're going to use the statistical software to conduct the analyses. The steps for computing Spearman's row in JASP are pretty much identical to what we did with Pearson's R. We just have the added step of checking the box for Spearman's row. As we saw with Pearson's R, the degrees of freedom for Spearman's row are n-2. So summarizing the results of Spearman's row correlation are also very similar to what we saw with Pearson's R. Here's an example. Note that the R subscript S stands for Spearman's row here. So we could say that there was a perfect positive correlation between the number of hours that the student worked and the grade received. So R subscript S, okay, for Spearman's row equals 1. So that means perfect, positive. Correlation, comma, P less than 0.001. Now we're going to discuss some other common correlations besides Pearson's R and Spearman's row, which are among the most commonly or frequently used correlational methods in psychological research. There are several other correlation coefficients that you should be familiar with. These coefficients can be used under different circumstances. So you may encounter these when reading published research articles. Moving on to page 14. So we have Kendall's tau. So like Spearman's row, Kendall's tau is a non-parametric correlation coefficient. All right, so there we see number 1 is Kendall's tau. It is a non-parametric correlation coefficient. Kendall's tau is particularly useful for ordinal level data with small sample sizes. So compared to Spearman's row, Kendall's tau performs better in these cases where there are repeated data values which lead to ties in the rankings. Kendall's tau looks at how well the rankings of the two variables match up by counting pairs of data points. So if both variables increase or decrease together, then the pair is called concordant. If one goes up and the other goes down, it's a discordant. This method of counting pairs helps Kendall's tau give a more accurate measure of the relationship, especially when there are many ties. So most statistical programs like JASP can calculate Kendall's tau. However, it is not used as frequently as Spearman's rho, so we're not going to actually go into details of how it's calculated here. The important thing to remember is that Kendall's tau is useful when you have ranked data and you want to see how two sets of rankings compare, especially if your data set is small and has many ties. Like Pearson's R and Spearman's rho, Kendall's tau ranges from -1 to +1. A value of +1 means a perfect positive relationship, and -1 means a perfect negative relationship. 0 means no relationship. So we're moving into section 10.4.2. So the phi coefficient and Kramer's V. So far, again, we're on page 14 of 17. So far, of all the correlational coefficients we've seen, they require data to be measured on at least an ordinal level scale. But what if our data are nominal, right? So that's where the phi coefficient and the Kramer's V come into play. So the phi coefficient is a measure of the association between two binary variables. Now, binary variables are a special type of categorical variable that have only two categories, like yes or no, correct or incorrect, male or female, right? The phi coefficient is calculated using a 2x2 table. And this table shows the frequency of each combination of the two variables. So for example, let's say we want to see if there is a relationship between whether students do their homework, like yes or no. Right, so we want to see if there's a relationship between whether students are doing their homework, like yes, they did it, or no, they did not, and whether they passed a test or failed a test. So we can create like a 2x2 table with the counts of students in each category. The phi coefficient will tell us how strong the relationship is between doing the homework and passing the test, okay? So the value of the phi coefficient ranges from -1 to +1, where the +1 indicates a perfect positive relationship, okay? The -1 indicates that perfect negative relationship. 0 indicates no relationship. With the Kramer's V, this is another example or another measure of association. And but it can be used with variables that have more than two categories. So it's an extension of the phi coefficient that can be used with larger tables. So for example, let's say we want to see if there's a relationship between a student's favorite type of pet, like a dog, a cat, or a bird, and their favorite subject in school, like math, science, or English. So we can create a 3x3 table with the counts of students in each category. Kramer's V will tell us how strong the relationship is between the type of pet and the favorite subject. So unlike other correlation coefficients we've seen, the value of Kramer's V ranges from 0 to 1, where 0 indicates no relationship and 1 indicates a perfect relationship. So both the phi coefficient and the Kramer's V help us understand the strength of the relationship between categorical variables. They're important tools in statistics, especially when you're working with data that can be divided into the different categories or different groups. We will see again in later chapters how to, again, we will see in the later sections of this book when we learn about categorical data analysis. We will see the phi coefficient, the Kramer's V, right? And we're also going to later on see the chi-square test. This next section is on correlations as well. So we're still on page 14 of 17. We're in section 10.4.3. So this author says that when they were in graduate school, they learned they called tetrachoric, polychoric, and point biserial correlations. I think I have a typo here. Hold on. I do have a typo. Hold on. Tetrachoric, polychoric, point biserial correlations. There you go. So when this author was in graduate school, they're saying that they called tetrachoric, polychoric, and point biserial correlations special correlations. We're not going to get into the calculations of these in this particular introductory session, but I do want you to be aware that they exist in case you come across them in the future. So like when you're reading like a published research article, these are used in cases where we measure a variable on an ordinal level scale or as a binary variable, but we have reason to believe that the underlying construct is actually interval ratio and continuous. So for example, a course may be graded as pass-fail, but we know course performance is actually continuous. So let's talk about tetrachoric correlations. These are used when we want to measure the relationship between two binary variables that are assumed to have underlying interval ratio continuous distributions. So for example, let's say we want to see if there's a relationship between whether students are passing or failing a test and whether they like or dislike math. So even though pass and fail and like and dislike are both binary, we might believe that these choices come from a more complex underlying scale of ability or preference. So in other words, we should have measured in this on like an interval or a ratio continuous scale, but we didn't. Moving on to page 15. So the tetrachoric correlation is different from the phi correlation that we saw, in that the tetrachoric correlation is actually trying to estimate what Pearson's R would be if we had measured both variables on an interval or ratio continuous scale. Polychoric correlations are similar to tetrachoric, but they can be used with ordinal level variables with more than two categories. So, for example, let's say we want to see if there's a relationship between how often students do their homework, like never do their homework, sometimes do it, often do it or always do it, and then their grades, like A, B, C, D, or F. So both of these variables are ordinal because they have a natural order. And while they're measured on ordinal level scales, there is reason to believe that the constructs underlying both are actually interval and ratio, and continuous. So for example, how often students do homework could have been measured in hours or minutes, and grade could have been more precisely measured as points. The polychoric correlation is different from Kramer's V. Yes, the polychoric correlation is different from Kramer's V, which is also used with two ordinal level variables, and that the goal of the polychoric correlation is to estimate what Pearson's R would be if we had measured each variable on an interval or a ratio continuous scale. And finally, the point biserial correlation is used when we have one binary variable and one continuous interval or ratio variable. So here's an example. We could use this example. So we could use this to compute the correlation between whether a student submitted their homework like yes or no, which is your binary variable, and then their score on the exam, which would be the one continuous interval or ratio variable. So we could go on for days, says this author, about all of the different correlation coefficients, right? So as you're reading psychological research, Pearson's R is by far the most common correlation coefficient that you're going to come across, followed by Spearman's rho. But there is a good chance that you'll also see a phi coefficient, a Kramer's V, one of the special correlations like a tetrachoric, polychoric, or a point biserial correlation. So again, there's a good chance that you'll see one of those special correlations, a phi coefficient, a Kramer's V, or one of the many other correlations that exist that we didn't talk about. So if you come across one that you haven't seen before, we can Google it. Most correlations will range from -1 to +1, but as we saw with Kramer's V, there are some exceptions. A quick Google search will give you a quick overview and the information that you need to interpret any new correlations that you come across.